Okay, let's unpack this. We all interact with AI now,
Oh, definitely. Every day.
whether it's like a quick search or uh, drafting an email, maybe asking for creative ideas.
Mm,
These large language models, they're just woven into our daily lives now.
totally integrated.
And yeah, we might see, a monthly subscription fee, maybe an API cost. But what if I told you there's this whole hidden ledger of costs, stuff you're actually paying, whether
Yeah.
you realize it or not?
Mm-hmm.
We're talking about the true, often unseen costs,
Mm-hmm.
computational, environmental, even the economic burden of every single query you make to an LLM. It goes way beyond just the bill.
That's absolutely right. And our mission, really, in this deep dive is to pull back the curtain on those invisible costs.
Yeah.
We've really been digging into some fascinating doctoral level analysis, actually, and it fundamentally challenges how we've typically thought about AI's impact.
How so?
Well, for a long time, the conversation was almost exclusively about the colossal, one-time energy hit of training these massive models, huge numbers.
Right. I remember seeing figures for things like GPT-3.
Exactly. But the research now, it overwhelmingly points to a completely different ongoing burden, something called inference.
Inference, okay.
That's the continuous process. It's where the model generates a response to your query every single time you ask it something.
Oh, okay.
So get ready for some truly surprising facts about what happens behind the scenes every time you hit enter.
So let's start there then, shifting our perspective.
Yeah.
Historically, like you said, when we talked AI's environmental footprint, it was all focused on that huge upfront energy cost, training.
This initial hit, yeah.
You mentioned GPT-3. Training that one model, I think I read it, consumes something like, 12,287 megawatt hours of electricity.
Staggering numbers.
And that translates to like hundreds of tons of CO2 equivalent going into the atmosphere, plus massive amounts of fresh water just for cooling, something like 700,000 liters.
Yeah, the scale is immense. But the key thing was it was seen as a finite one-time investment.
Right. Once it's trained, that cost is sort of sunk, paid for.
Kind of, but that's definitely no longer the full picture. Not even close, really.
Okay.
What's truly fascinating here is how dramatically that picture has changed. The crucial shift is to inference, like I said. That's now the dominant, ongoing cost.
Right. Not the training anymore.
Well, training is still huge, but inference overshadows it over the model's life. While training is a finite, one-time capital investment, inference is continuous and at a planetary scale.
Wow. Planetary scale.
Yeah. The research indicates it now accounts for as much as 90% of a model's total life cycle energy consumption.
9%. So almost all of it is happening after training.
Over the lifetime, yes. And here's a significant challenge. The companies, the commercial AI providers, they're incredibly opaque about this.
You can't just look it up.
Not really. There are almost no standard methods to quantify these per query costs, which means researchers, they have to rely on complex assumptions, about hardware like NVIDIA H100 GPUs, maybe assuming 10% utilization, just to even estimate them.
So it's kind of a black box for the public.
A real black box.
Yeah. Okay, so if inference is where the real action is, the real cost,
Mm-hmm.
what's actually happening under the hood when I type a query? What are the bits chewing up all this energy?
Great question. So basically, most modern LLMs are built on what's called the transformer architecture.
Where did that?
It's known for its self-attention mechanism. That's basically how it figures out which parts of your input are most important for understanding the context.
Okay.
Now, the model's complexity, that's often measured by its parameters, billions, sometimes trillions, of these adjustable settings.
Like the huge numbers you hear about.
Exactly. And crucially, when you type something in, the model doesn't see raw text. It converts it into numerical codes called tokens.
Tokens, okay.
A token could be a whole word like hello, or just part of a word like trans and former, or even a single character.
Got it.
And the total count of these tokens in your input and also in the output it generates. That's a primary driver of the computational work. How much number crunching needs to happen.
So more tokens generally means more work.
Generally, yes. And what's wild is how that simple count can have these massive hidden consequences we'll definitely get into later.
Okay, intriguing.
Yeah.
So when we start looking at the actual energy consumed per query, what do those numbers tell us? Is it a lot? A little?
Well, what's truly eye-opening is the sheer range of energy consumption. It varies hugely. So for a, let's say, short query on a pretty efficient model like OpenAI's GPT-4o, it might sip around 0.43 watt hours. That's but
0.43 watt, that sounds small.
it sounds small. Yeah, that's kind of a baseline for a typical quick interaction.
Oh,
But
there's a but.
there's always a but. If you ask for complex reasoning tasks using more advanced, maybe specialized models like OpenAI's O3 or DeepSeek R1, a single, maybe long prompt query, that can exceed 33 watt hours.
Wait, from 0.43 to over 33?
Exactly. More than 70 times the energy.
Whoa, for one query.
For one complex query on a powerful model. So the key insight here is really stark. Your choice of model and the complexity of what you're asking it to do dramatically dictates the environmental cost.
So it's not like every AI interaction costs the same. Not even close.
Not even remotely close.
Okay, so models are getting more efficient per query. That 0.43 number sounds better than maybe older models. That's good news.
Okay.
Right. Or is there a catch? A larger paradox, maybe?
Here's where it gets really interesting.
Oh.
It's what the research calls the scale paradox.
Scale paradox. Okay.
We're seeing this phenomenon where, yes, the per-query efficiency of AI models improves, they get better, leaner, but the overall consumption just explodes.
Why? More people are using it.
Exactly. It's increased adoption and usage. Think about it. A single 0.43 watt-hour query to GPT-4o, it seems trivial, right? Insignificant.
Yeah, on its own.
But then you scale that up. You scale it to an estimated 700 million daily queries globally, which is, a plausible direction we're heading.
700 million a day.
Yeah. Suddenly, the cumulative annual impact becomes truly staggering.
And when you say staggering, what does that actually look like? Can you put that in real terms?
Okay, so that level of aggregated electricity consumption, we're talking comparable to powering roughly 35,000 U.S. homes annually.
Okay.
The water consumption, mostly for data center cooling for those queries, that matches the annual drinking needs of about 1.2 million people.
Just the water for cooling.
Just for the cooling. And the resulting carbon emissions, you'd need a forest roughly the size of Chicago to soak that up each year.
A forest the size of Chicago every year.
Yeah.
Just from people asking questions.
It's an immense, often silent drain on resources, hidden in plain sight.
Okay, so that's the energy, the environmental side.
Right.
But how does that translate into, economic costs for the companies running these things and maybe ultimately for us users?
Well, first you've got the direct API fees. Those are the most visible costs, right?
You need to pay per token or something.
Exactly. So processing, say, 1 million input tokens and 1 million output tokens with something like GPT 3.5 Turbo, that might cost you around $3.50.
Okay.
But do that same volume with the more powerful GPT-4, you could be looking at about $90.
$90 versus $350. That's a huge jump.
A 25-fold increase, yeah, for the same volume, just a more capable model. But then providers, they bear these immense indirect costs too.
Like what?
Hardware, for one. A single high-end cloud server instance, packed with the latest GPUs, that can run over $23,000 per month, just one server.
Ouch.
And then there's the electricity bill for the data centers themselves. Industrial rates, they typically range from maybe 0.06 cents to $0.09 per kilowatt hour. It adds up fast.
Yeah, I bet.
And what's even more telling, maybe, is looking at open source models. For the same model, like Meta's Llama 3.170B, you can see more than 10 times price variations across different cloud providers.
So the exact same model.
For the exact same model, sometimes from 0.2 thousand per million tokens up to $2.90.
So that difference isn't just the raw cost of running it.
Not entirely, no. It highlights that pricing isn't just about cost recovery. It's about profit margins, market positioning, competition, a whole lot more.
So the economic picture is pretty complex, pretty stark. But those watts we're talking about, those dollars, they're kind of two sides of the same coin when it comes to the environmental impact, right?
Let's dig into the carbon and water more.
Absolutely. They're deeply linked. The carbon emission calculation is, fairly direct on paper. It's your energy consumption in kilowatt hours.
Right.
Multiplied by the data center's power usage effectiveness, or PUE.
PUE, what's that?
PUE basically tells you how much extra energy the data center uses for things other than the computers themselves, mostly cooling, lighting, power conversion losses. A PUE of 1.0 would be perfect, meaning zero overhead.
And are they close to that?
The big players like Google and AWS report really excellent PUEs, like 1.08, 1.09. Very efficient facilities.
Okay, so energy x PUE. Then what?
Then you multiply by the grid carbon intensity of the region where the data center is located.
So where the power comes from matters a lot, hugely. The U.S. national average is around, say, 367 grams of CO2 equivalent per kilowatt hour. But if your data center is in France, which uses a lot of nuclear and renewables, it might be way lower, like 81.3.
Wow.
But if it's somewhere heavily reliant on coal, like parts of China, it could exceed 1,000 grams per kilowatt hour. Same computation, vastly different carbon footprint depending on location.
That's a massive variable. And the water. You mentioned that staggering figure earlier.
Yeah, that massive water footprint, primarily for cooling those data centers, equivalent to the drinking needs of 1.2 million people annually, just for those hypothetical 700 million daily queries. It's a huge, often overlooked environmental cost.
Okay. If we connect this to the bigger picture, maybe try to make these costs even more tangible. Do you have any fun comparisons? I know it's not really fun, but you know what I mean.
Yeah. Fun might be stretching it, but let's try. If we connect this to the bigger picture, think about this.
Sure.
Remember that single complex reasoning query, the one that could hit 33 watt hours? That consumes significantly more energy than fully charging a modern smartphone, which is usually around 20 watt hours.
So one complex question uses more power than charging my phone.
Yep. And just 2 such queries, maybe around 66 watt hours total, that actually exceeds the energy you need to boil a full liter of water in an efficient electric kettle, which is about 60 watt hours.
Boiling water. Okay.
Yeah.
That starts to feel more real.
Right. And for carbon, let's say you spend an hour doing some creative story writing with a model like GPT-4, maybe it generates a couple thousand tokens. The energy cost for that hour is roughly equivalent to driving an average car about 1.75 meters. So like 5.7 feet.
Driving 5 feet. Seems small, but maybe it adds up.
It does when you think about how many people are doing it. Or look at it this way. You'd need to make over 2,200 of those short 0.43 OH GPT-4 queries just to equal the emissions of driving a single mile in a typical car.
2,000 queries equals 1 mile driven. Okay, that puts it in perspective.
It's all about that scale again.
So, given everything we've heard, the prices, the energy use, the environmental impact, is there a fundamental mismatch? Like, between what we're paying for AI, maybe in dollars, and its true cost, especially environmentally?
That's a great way to put it. The research really highlights this significant disconnect between price, cost, and value.
Oh.
The API price you pay for a model, it's often a really poor proxy for its actual environmental cost.
Meaning cheaper doesn't necessarily mean greener.
Exactly. You might see 2 models on a cloud platform, similar pricing, maybe even similar parameter counts, right? And you'd assume their operational costs, their energy draw, are comparable.
Yeah, seems logical.
But the research shows that models with similar sizes can have vastly different energy consumption profiles. It depends on their underlying architecture, how well they're optimized, lots of factors. So this means that as a user, you basically cannot reliably use the price to pick the greenest model.
So if I wanted to be environmentally conscious, just picking the cheapest option won't work.
It might or it might not. There's a huge information gap. You're effectively flying blind if sustainability is a factor in your choice.
Okay, that's already a lot to digest. The scale, the hidden costs, the pricing disconnect. But now, you mentioned something earlier that sounded really surprising. A hidden cost from spelling mistakes. How on earth does that work?
Yeah, it's fascinating, right? And kind of counterintuitive. It comes down to tokenization.
Okay, remind me what that is again.
So when you type text into an LLM, the first thing it does is break that text down into numerical IDs, the tokens we talked about.
Right.
Now, an efficiently designed tokenizer, it assigns single tokens to common words. Things like language or computer probably get 1 token each.
Makes sense.
But when you have what are called out-of-vocabulary words or OOV words, like a typo.
Like if I spell strawberry wrong.
Exactly. Strawberry might be 1 or maybe 2 tokens normally, but if you type strawberry with 1 R, the tokenizer probably doesn't have a single ID for that misspelling.
So what does it do?
It has to break it down into smaller pieces it does recognize. Maybe straw, burr, why. So suddenly, your single misspelled word becomes 3, maybe even more tokens.
Oh, so a typo directly increases the number of tokens.
Directly increases the length of the token sequence your input generates.
Okay, I see that part. But why does that matter so much for cost?
This is where the underlying architecture really bites you. Remember the transformer architecture and its self-attention mechanism.
Yeah, the part that figures out context.
Right. To do that, it basically calculates an attention score between every single token in the sequence and every other token.
Every token compared to every other token.
Every single one. So if you have L tokens, the number of comparisons isn't proportional to L, it's proportional to L squared.
L times L.
Squared. So it grows much faster than the length.
Exactly. That's the crucial bit. The computational complexity explodes. It scales quadratically with the length of the input sequence. We write it as OL.
OL. This means doubling the length of the token sequence doesn't just double the computational work, it roughly quadruples it.
Whoa.
Every extra token you add makes the model work disproportionately harder. That's why the transformer architecture is particularly sensitive to the input length.
Okay, now I see it. Typos make more tokens. More tokens hit that quadratic scaling,
Bingo.
and suddenly my little spelling mistake cost way more energy.
Exactly. You can see how these two concepts combine to create what the research paper calls the tokenization tax.
The tokenization tags.
Yeah.
I like it.
A typo leads to more tokens, which then leads to a quadratically greater number of computations. And that directly translates to increased energy consumption and higher latency, a slower response for that specific query.
Oh.
It's literally a computational penalty for input imprecision.
Can you give some examples? Like, how bad can it be?
Oh yeah, the paper had some vivid ones. Take the name Kolmogorov, the famous mathematician.
Okay.
Normally, with a good tokenizer, that's one single token, one unit of work, basically. But misspell it slightly, maybe as Kolmogorov swapped the O and E. Suddenly, that can become 4 tokens.
One token becomes 4, just from swapping 2 letters.
Yep. That's a 300% increase in the number of tokens, and thus a much bigger hit on computation for that single word.
Wow. Any others?
Yeah, like pronunciation. That's usually 1 token. But the common misspelling pronunciation with the extra O-U-N, that can become 3 tokens. A 200% increase, just from 1 extra letter.
That's actually kind of mind-blowing. Such a small error, such a big potential impact computationally.
It really is.
So thinking bigger picture then, what are the broader macro implications of this seemingly tiny micro cost? This raises an important question, right? Especially when we think about language diversity globally.
This raises an important question indeed. It's a really crucial point. It reveals that the operational efficiency of this entire global LLM ecosystem is highly sensitive to the, let's say, statistical properties and the cleanliness of the language it processes. Meaning these tokenizers, they are overwhelmingly optimized for clean, standardized English. That's the bulk of the data they were trained on.
Okay.
So any deviation from that standard, think about slang, regional dialects, technical jargon, specialized terms, or especially non-English languages.
Yeah.
They all tend to be tokenized less efficiently. They get broken into more pieces.
So it takes more tokens to say the same thing if it's not standard English.
Often, yes. For instance, the research points out that some languages can require up to 15 times more tokens per word than English when using these standard English-optimized tokenizers.
15 times.
Yeah, which has these subtle but really important implications for fairness and accessibility.
How so?
Because it means users who communicate in non-standard ways or in languages other than English are effectively paying a higher computational price for their interactions.
And therefore a higher environmental and financial price too.
Exactly. It's this invisible burden, this hidden tax placed on non-standard or non-English communication within the current AI ecosystem.
That's a truly thought-provoking point. A hidden bias, almost, built into the efficiency.
Okay, wow. Now let's uncover another counterintuitive cost driver you hinted at. Not the input, but the length of the generated output. Why is the model's response length so significant? You said even more so than input length or task complexity.
Yeah, it often turns out to be the single most significant driver of inference energy consumption. More than how long your prompt was, sometimes more than how hard the question was.
Why is that? Why does the output matter more than the input?
It's because output generation is a fundamentally different process. It's sequential or autoregressive.
Autoregressive.
Meaning it generates the response 1 token at a time. It predicts the next token based on all the previous tokens it just generated. Token by token.
By token.
Like building a chain.
Precisely. And because it has to do this step by step, it keeps the GPU, the main processor doing the work, actively engaged in computation for a much longer duration compared to just processing your initial prompt all at once.
Okay, so the longer the chain it builds, the longer the GPU is running hot.
Exactly. More tokens out means more time computing, which means more energy used.
So that engineered chattiness we often see, when the AI gives you a long preamble before the actual answer, for user satisfaction, that must have a big impact then.
It absolutely does. This
Ah,
leads directly to the cost of creativity and verbosity.
right.
Now, creative tasks like asking it to write a story or an essay, those are inherently long form. That makes sense. You expect a long output.
Sure.
But what's maybe more surprising or concerning is the deliberate engineered chattiness found in many consumer-facing LLMs. It's designed, as you said, for user satisfaction to make it feel more helpful or conversational.
Like when it says, certainly I can help with that. Here's the information you requested.
Exactly that kind of stuff. One study mentioned in the source analysis found that the minimal core answer, just the facts, constituted only 42% of the total response length on average.
Only 42% was the actual answer.
Yeah. The remaining 58% was just conversational filler, politeness routines, summaries of what it was about to say.
Wow. So more than half the output was fluff.
Essentially, yeah. And while it might feel more human or user-friendly to some, it effectively doubles the energy consumption, the financial cost via API fees, and the environmental footprint of that query, compared to just giving a concise, fact-only answer.
It's just doubled the cost for politeness.
Pretty much, a deliberate design choice with a significant consequence.
And that chattiness, or maybe necessary verbosity, plays a big role in those really high-cost reasoning models too, right?
Mhm.
The ones you said could hit over 33 watt-hours per query.
Precisely. Models like OpenAI's O3 or DeepSeek R1, they often use what's called a chain of thought process.
Big if thought.
Yeah, they explicitly write out their logical steps, their reasoning process as part of the output. First, I need to understand X, then I need to calculate Y, that kind of thing.
Ah, showing their work.
Exactly. Which is incredibly powerful for solving complex problems. But naturally, it generates extremely long outputs.
Makes sense.
And this necessary verbosity is a key reason why their API pricing is often much higher. For example, the analysis mentioned O3 could be around $40 per million output tokens, compared to maybe $2 for output from GPT 3.5 Turbo. A huge difference driven by output length.
Okay. And it's not just the generation of the output that's costly, right? I think I read somewhere that the output itself can have a downstream energy cost. Like if the LLM generates computer code.
That's another fascinating layer, yes. The research points out that LLM-generated code, say in C++, say, can sometimes be significantly less energy efficient to execute than an equivalent solution written by an expert human programmer.
So the code the AI writes might actually use more power when you run it.
Yeah, in some cases studied, it consumed up to 132% more energy to run. So it adds this whole other downstream cost. Not only was the generation itself expensive, but the output, the code it produced, might be less efficient in its own operation.
Wow. So what does this all mean when we put it together? This high environmental cost, we're discussing the energy, the water, the carbon. Is this just an unavoidable technical necessity of powerful AI, or is it something else, a choice?
So what does this all mean? That's the million-dollar or maybe the multi-megawatt-hour question, isn't it?
Yeah.
The analysis strongly suggests that a significant portion of this high environmental cost is not an unavoidable technical necessity. Rather, it seems to be a direct consequence of deliberate design choices.
Choices made by the developers.
Yes. That verbosity, that conversational filler, that specific style of interaction we've come to expect from many AI models, that's a feature. It's been specifically engineered, presumably, to enhance user experience or perceived helpfulness.
But it comes at a cost.
It's a clear, albeit often unstated, trade-off. Prioritizing a certain kind of user interaction, a certain personality, at the direct expense of greater energy consumption, higher financial cost, and a larger environmental footprint.
Okay. Given all these costs, the scale, the hidden factors like typos, the deliberate verbosity, it sounds pretty daunting. Is there a clear path to efficiency? Or are we kind of stuck with this high environmental price tag for our AI convenience?
Well, it's certainly a major challenge, but it's definitely not all doom and gloom. There's an intense amount of research and effort underway to mitigate these impacts.
Okay, good.
Though the consensus seems to be there's no single magic bullet solution here.
Right, it's never that easy.
No. What's really needed is a holistic, system-wide, or sometimes called a full-stack approach to achieving what's being termed green AI.
Green AI, okay. So where do we start? Does it start with us, the users?
Actually, yes. One of the most accessible optimization techniques really does start with us, the user, through something called prompt engineering.
So how I write my prompt can genuinely make a difference to the energy used.
Absolutely. It sounds simple, but just instructing the model to be concise or maybe provide only the minimal answer or don't include conversational filler, things like
Yeah.
that. That alone can lead to significant energy savings, potentially in the range of 25 to 60%, according to some studies.
25 to 60% just by asking to be brief.
Yeah. The source analysis highlights one strategy that achieved a 58% reduction in energy consumption by demanding conciseness. And interestingly, it actually improved the factual quality of the response too, presumably by cutting out the noise.
So less energy, better answer. That's a win-win.
Definitely a win-win, and something anyone using these tools can try right now.
That's actually really empowering. Okay, so that's user level. What about the model level itself? What are the AI engineers doing to make the AI inherently more efficient?
Great question. At the model level, there are several key techniques being actively developed and deployed. One is quantization.
Quantization sounds technical.
It basically means reducing the numerical precision of the model's parameters. Think of it like saving an image with fewer colors. You go from, say, 32-bit numbers down to 8-bit numbers.
And that helps how?
It shrinks the model's memory footprint, speeds up computation because the numbers are simpler, and directly lowers energy use.
Okay, makes sense. What else?
Then there's pruning. This is kind of like trimming a hedge. You identify and remove redundant or less important parameters, the connections within the neural network that don't contribute much.
So you make the model smaller, leaner.
Exactly. A smaller model means less computation, less energy. And another really powerful one is knowledge distillation.
Knowledge distillation, like bottling wisdom.
Kind of. You use a large, powerful teacher model to train a much smaller student model to mimic its behavior on a specific task.
Transferring the knowledge to a smaller brain.
Precisely. And this can be incredibly effective. It's capable of reducing the model size by up to 90% in some cases and cutting that inference energy consumption by 50–60%. Huge savings.
Wow, this is big numbers.
Yeah.
Okay, so we've got user prompts, model optimization. What about the core design? The architecture and algorithms, are they tackling that quadratic explosion thing you mentioned, the OL?
Yes, absolutely. That's a major focus of architectural and algorithmic innovations. Researchers are actively developing more efficient alternatives to the standard transformer architecture to tackle that OLL bottleneck.
Like what?
Well, the analysis mentions things like the reformer model, which uses clever tricks to reduce the complexity down to something near linear, think OL log L instead of OL, that allows for much longer sequences to be processed much more efficiently.
So less sensitive to input length.
Much less sensitive. There are also optimized attention mechanisms, techniques with names like multi-query attention or grouped query attention. These aim to reduce the amount of data that needs to be moved around in memory during the attention calculation, which is often a bottleneck. Less memory movement means faster processing, greater efficiency.
Okay, lots happening at the algorithmic level too. And then right down at the bottom, the hardware, where the models actually run. Are there strategies there?
Definitely. This involves hardware and deployment level strategies. One obvious one is hardware-specific optimization, using specialized AI accelerator chips like Google's TPUs or the latest NVIDIA GPUs, which are just built specifically for these kinds of matrix multiplication.
Using the right tool for the job.
Exactly. Another fascinating technique is dynamic voltage and frequency scaling, or DVFS.
DVFS.
Yeah. This allows the system to adjust the GPU's clock speed and voltage in real time based on the current workload. Kind of like dimming a light bulb when you don't need full brightness. This can reduce energy consumption significantly, maybe 30–50%, compared to just running the GPU full blast all the time.
Smart. Adjusting power based on need.
And finally, there are efficient serving techniques. This involves software like systems called VLOM or NVIDIA Triton Inference Server. They use clever methods like continuous batching to pack more user queries onto the GPU simultaneously, keeping it highly utilized.
Maximizing throughput.
Right. And techniques like speculative decoding, which tries to guess the next few tokens in advance, potentially speeding things up and reducing latency and cost. Lots of software smarts involved too.
Okay, so it sounds like there are potential improvements at every single level. User model, algorithm, hardware, deployment software.
Every level, yes.
But what's clear, I guess, is the system level challenge.
Yeah.
You said there's no single magic bullet for green AI. It sounds like all these pieces need to work together.
That's precisely it. That's the crucial takeaway. These different layers, user behavior, model design, algorithms, hardware, software, they're all deeply interdependent.
Meaning one affects the others.
Exactly. An optimization made at one layer can be either amplified or potentially even negated by choices made at another layer.
Can you give an example?
Sure. A concise prompt from a user that's a user-level optimization can significantly amplify the energy savings you get from running a highly quantized model that's model level on an efficient GPU using DVFS that's hardware level. They work together. Right. Conversely, if a user keeps asking for extremely verbose outputs, that could potentially wipe out the energy savings gained from a super efficient new algorithm.
So it really demands thinking about the whole picture.
Exactly. Achieving truly green AI demands co-design and co-optimization across the entire stack, from the way you freeze your prompt all the way down to the silicon chip it runs on.
Okay. So to kind of wrap up our deep dive here, we've seen that the true costs of AI, they've really shifted, haven't they? It's not just about that massive one-time training cost anymore.
No, the focus is now squarely on inference.
Right. It's about the continuous global impact of every single query, every interaction you have. And the cost of a query isn't some fixed number. It's incredibly dynamic. It changes based on your choices, the task complexity, the model's design.
Highly variable.
We explored that scale paradox where individual efficiency gains are being swamped by just the sheer explosion in usage.
A crucial point.
We uncovered that fascinating hidden tokenization tax, showing how even a simple typo can create this unseen computational and therefore energy burden.
The cost of imprecision.
And maybe most critically, we revealed that a lot of AI's current environmental impact isn't necessarily unavoidable. It's often a deliberate trade-off, prioritizing a certain chatty user experience at the expense of efficiency.
A design choice with consequences.
But thankfully, there is a path forward. It requires this holistic, multi-layered approach to efficiency, involving everyone from users to hardware designers.
That's right. And thinking about that path forward, this really highlights an urgent need. We desperately need the development and adoption of standardized, transparent environmental reporting for AI models.
Like nutrition labels, but for AI energy use.
Exactly. Think about how helpful energy efficiency ratings are for household appliances. Your fridge, your washing machine.
Yeah, that the guide choices.
Imagine if every LLM, whether it's open source or proprietary, came with clear, comparable metrics. Information on its typical energy use per query, its water consumption profile, its carbon intensity based on where it's typically hosted.
That would be a game changer.
It really would. That kind of transparency would finally empower you, the consumer, and also developers building applications to make genuinely environmentally conscious choices.
And it would push the providers too, right?
Absolutely. It would incentivize providers to compete not just on performance and price, which they do now, but also on environmental efficiency, making greenness a competitive advantage.
So maybe a final thought for our listeners.
Yeah. The next time you interact with an LLM, just take a moment. Think about that invisible ledger ticking away behind the scenes, the computation, the energy, the water, the carbon. Consider the complexity of your query, the length of the response you're getting. Even maybe double-check your spelling. Knowing what you know now, what might you do differently?